All right, good morning, everyone. Welcome to our last lecture. So today, I don't have any new course content to share. My plan for today is to make a few announcements, talk a little bit about grading and maybe some big picture stuff, and then open the floor to questions from you. So some people have already been asking questions on chat about course content that I'm going to try to address today. Please post your questions in chat and I'll try to answer them. And I'm happy to answer questions for exam review. So our exam is next Tuesday. Our final exam is next Tuesday. I'll talk a little bit more about that and the format of that in a second. But you probably already saw, if you're in the class, you saw that I posted a huge document of practice questions for the exam. So my suggested technique for studying for the exam, which I mentioned before, but I'll mention again, is to just start going through this document, talk over the questions with your friends, and anything that you're stumped on, uh, you can ask us, the course staff, on Slack, or if you have questions that you're already confused about, you can ask right now in this lecture. So let's get started. So what do I want to say to you today? Well, first of all, one thing that I want to say is that I'm proud of you. This quarter has been tough. This year's been tough. What have we had to deal with this quarter at UCSC? Well, this was my second year. Second year is supposed to be easier than the first, but let's see. We had lots of public safety power shutoffs. There were strikes. The grad students went on strike. There were other strikes as well. Most visibly, the grad students went on strike. I support the grad student strike, by the way. I'm happy to talk to people about that. Uh, uh, but that's a topic for another time. Obviously, the global pandemic. Um, and then the last few days, we've been uh, uh, in the middle of a nationwide epidemic of police brutality, and so this year has been rough, and especially for those of you who are seniors, which is the majority of the class. You don't even get a graduation ceremony, not a real one. So it's kind of unfortunate, right? Your college experience does not get to end in the way that you had surely hoped that it would. So I'm very proud of you all for your incredible resilience in the face of everything that you've had to deal with. And it's clear that a lot of you have learned a lot in this class despite the circumstances. So I've been very impressed by the questions that some of you have been asking and the comments that some of you have been sharing. And I hope that you got as much out of this class that I have gotten out of teaching it. Um, uh, so the first thing I guess that I want to say is that I'm proud of you. On that note, course evaluations, sets are happening. So do them, please. This is something that I've been I've been here for 2 years, as I mentioned, and every quarter the response rate for sets gets lower. So it was pretty good my first quarter here, fall 18, and then every quarter it's gotten a little bit lower. And I can try to wheedle you and nudge you to complete them, and even like dangle a carrot. Like last quarter, I told the students that I would make balloon animals in class if a certain percentage of the class filled out sets. I'm really bad at making balloon animals, so it would have been hilarious. But I don't. So why should you actually do this? Like, why am I nudging you so hard to do this? Well, it actually matters in terms of reappointment and promotion and tenure time. So I've even in the short time that I've been here, I've been able to participate in the process for a few promotion cases, and it's always the it's always the case that what people write on sets is relevant. So this is one of the few times, I don't know if you know what happens with your course evaluations, with your sets when you fill them out, but not only do I read them, and they're completely anonymous, by the way, but not only do I read them, but my department chair in my department gets access to them as well. And they're used in decisions about how should courses be adjusted, who should teach what, and so on. And furthermore, okay, I mean, we can admit that some professors, especially professors who've been teaching for decades, their teaching style is pretty ossified, and they're probably not going to change how they teach. But I am still capable of changing, right? So if there are ways in which I can change to make the course better, I want to know what they are. And if there are things that I've done that you like and that you want to encourage, you should say so. So this is really important to us. So please don't continue the downward trend. Try to reverse the trend. So it's down. It's really invisible, guys. It's something like 20% response rate now. Try to do better than that. It would be awesome if we could get like a 25 or 30% response rate at least for these. I know it's not exactly your top priority right now. But if you can take 10 or 15 minutes to do it, you don't even have to answer every question. But even if you can take 10 or 15 minutes to do it and just even give a cursory answer to some of the questions, that would be great. All right. Enough about that. Grading. So let's talk a little bit about grading. So all of you have seen this before, but I'll share the grading scale for the course, just as a reminder. So here's the official grading scale. So the in-class quizzes that we've done almost every day are worth 10% of your grade. And those aren't graded on content, by the way. They're only graded on if you fill them out. So if you literally wrote poop on every single in-class quiz, you would still get credit for it. The midterm was worth 20%, final 24%, the project 46%. So let me talk about this for a second. So first of all, this 10% for the quizzes, we're being very lenient with this. So we did 21 quizzes. The first one everyone gets credit for because the first one I forgot to even collect email addresses. So there's 21 quizzes. We're going to say everybody gets a few for free. So if you filled out 21 quizzes or 20 quizzes or 19 quizzes, you get full credit. After that, you lose a couple of points per quiz that you missed. So this means that something like 70% of the class gets full credit for these in-class quizzes, which I'm perfectly fine with. So those should be easy points. We have this policy that if your final exam score is higher than your midterm score, then the final score will replace the midterm. So for those of you who really struggled on the midterm for whatever reason, your final exam is an opportunity to redeem yourself. So in other words, so if this is the grading scale now, this what I'm showing right here, let's switch back to paper. So so if this is what it is, we will say that if you did better on the final, if you do better on the final than you did on the midterm, then the grading scale. So this is like option A. Option B is this. And we will pick whichever one of those options you do better with. Now, some people have asked if we can actually de-emphasize the final rather than emphasize it. And so I'm sympathetic to that, especially given how difficult everything has been in the last couple of weeks. So we're going to add a third option. So the third option looks like this. So it's 20% each for the exams and 50% for the project. So what we'll do is we're going to calculate your grade each of these ways and then give you the max. So this third option is intended to help people who are doing well on the project, but who, for whatever reason, struggle on exams. We don't want to get rid of the exam component altogether, and that's because there's very little opportunity in this course to really evaluate your individual performance. So the project evaluates how you do in a group, but a lot of people struggle with that for whatever reason. Maybe they ended up in a bad group, you know. So so we need a way to evaluate your individual performance, and the exams are kind of the only option to do that. So these are the choices. We're going to compute your grade in all of these ways, and then give you the best. So you don't have to pick one. We'll just automatically pick out whichever one is most beneficial for you. All right, that's about all I have to say about grading. In terms of, so somebody asked, how about an option to de-emphasize the project? So the main thing that I have to say about that is this. If you are really struggling on the project, you can ask for the option of getting it incomplete in the class. So you can't take an incomplete, so there's no way to make up the final later, right? So the final is the final, you can't do it later. But it is possible to take more time to do the project by asking for an incomplete. Let me warn you, so some students took an incomplete in the class that I taught last quarter. Incomplete means that you work with the professor to come up with a schedule to do the work, but it has to be done within a quarter. And if you don't do it within a quarter, your grade automatically turns into an F. So that works well for some people who are very disciplined and are able to kind of get the project done despite the fact that they have other stuff going on. But really, like, you probably want to be done with this chapter of your life, right? You probably just want to be done. So you can talk to me about that option if you want to, but I wouldn't recommend it unless you're extremely self-motivated. Okay, so that's it for logistical stuff that I want to talk about right now. Let's talk a little bit about distributed systems. So, like I said, we're not going to cover any new content today, but we are going to answer questions that people asked. So one question was, one of the questions on the review document I shared was, or the practice questions document, had to do with this idea of making copies for fault tolerance. So the question was, what are 2 or 3 ways in which making copies aids with fault tolerance. So the first thing we have to ask ourselves is, okay, fault tolerance, like what kinds of faults are we talking about? So we talked about several kinds of faults, right? We talked about crash faults, we talked about omission faults, we talked about Byzantine faults. Crash faults and omission faults are the ones that we're focusing on most in this course. Okay, so how does making copies help with those things? Well, what strategy did we talk about in this class for dealing with message omission? In other words, what is the strategy that we talked about for reliable delivery of messages? Somebody want to remind me? Okay, somebody just mentioned a couple of replication strategies, but we're just talking about the message omission. So the problem of a message getting lost somewhere between the sender and the receiver. How do you deal with that? Well, you deal with it by using a reliable delivery protocol. And a reliable delivery protocol involves sending multiple copies of the message until you find out that one got there, right? How do you find out that it got there? Because you get an acknowledgement. Um, so sending a message many times until at least one is acknowledged, or until one. So this is called at least once delivery. Do we have any way of guaranteeing that messages will get there exactly once? Probably not, right? Um, so if you do this, you might end up getting duplicates. That is something that you have to be okay with. If you want the message to reliably get there, you have to be okay with the fact that it might get there more than once. So that's one thing that we make copies of. We make copies of messages to deal with omission faults. So in addition to making copies of messages to deal with omission faults, what are some other things that we want to make copies of? Make copies of time when we share vector clocks. Interesting perspective. That wasn't exactly what I was thinking of. I was thinking of something a lot simpler, y'all. I was just thinking of making copies of data by replicating. So one reason why we do replication, why do we have more than one copy? Well, if one machine could crash, then we probably shouldn't have our data on just that one machine. So that's one reason why we might want to have another replica. So we can say dealing with machines crashing via replication protocols. Copying the same data in several distinct physical locations. Ideally, on different machines, and different machines that would fail independently, right? Because you really don't want it to be the case that all of your replicas fail at once, right? So you want to make failures as independent as possible. So maybe have them not only, you might want to have them in different data centers, right? Um, the trouble there is the farther apart that they are, the harder it is to do replication. So that's one of those trade-offs that we've spent the whole quarter talking about. The farther apart machines are, the harder it is to make sure that they agree. But the farther apart they are, the more fault tolerance that we have. We typically choose a compromise, right? We might choose to replicate over machines that are in the same data center, but aren't on the same server rack, something like that. We typically don't choose to replicate our data to a data center on Mars, even though that would indeed provide fault tolerance in case this planet is destroyed, right? Because replicating to and from Mars would be very slow. So you have to choose what kind of faults you're going to be tolerant of. Okay, so that's two. I said that there were two or three examples. So the last one I thought of is in the context of Mapreduce. So in Mapreduce, there's this computation that's being orchestrated by one node who's telling all of the worker nodes what to do, right? And if a worker fails, then they're never going to acknowledge to the master that it was done, right? So the master is going to have to decide what to do, and typically they're going to have another node do the work, right? So some work might get redone, some work might get duplicated. So So Mapreduce's way of dealing with some computation getting lost is to just redo it. And this ends up being the appropriate trade-off in many situations. So you could argue that it's inefficient, right? Because you're redoing work that was already done. And the alternative would have been for this, the machine that was doing this lost computation to very often save its work out to some place where the work would be safe, right? To the distributed file system. But that would be slow if that machine had to interrupt its work to periodically save its work out to the distributed file system. So instead, the compromise that they choose is this machine's work gets lost if it gets interrupted in the middle, and instead we just choose to recompute. There are always going to be, in a typical MapReduce computation, there's always going to be some redundant recomputation like this. Well, not necessarily always, but the longer the computation runs, the more likely it is that some part of it will fail this way. So those are three ways in which we make copies. So in the first scenario, we're dealing with the possibility of message loss by making copies of messages. In the second one, we're dealing with the possibility of crash faults by making copies of data. And in the last one, we're again dealing with crash faults by redoing computation. So perhaps these last two are somewhat related. But these are different ways in which we deal with faults by making copies. That's what I had in mind when I asked this question. Other questions? What else are you confused by? Paxos. All right. Um, hmm. So is there something specific that you want me to discuss here? Okay, let's talk about Paxos for just a minute, maybe more than a minute. So some big picture concepts in Paxos. So Paxos is a consensus protocol. Recall that a consensus protocol is a protocol by which participants can agree on a value. So each participant is allowed to contribute something. Let's say they're trying to agree on a bit. And the idea is that in the end, they're all going to agree. So either these are all going to be 0 or they're all going to be 1. Notice that they have to come up with that agreement among themselves. So there's no external process that comes along that says, you all have to be 0. The whole point of Paxos is that it's a decentralized algorithm, meaning that there's no single point of failure, which means that there can't be any kind of coordinator aside from these that's going to come in and tell them what to do. Now, they can choose to elect a leader among themselves, and they can and do choose to elect a leader among themselves in the sense that there's often a designated proposer, right? But there's no external process that's going to make that decision for them. So how does that work in the context of Paxos? Well, in Paxos, you're going to have some number of what are called acceptors, typically an odd number. So let's say we have 3 acceptors. Let's say for now that we just have 1 proposer, so I'll call it P1 here. Here's what happens. A proposer is going to start not by proposing a value, not by proposing one of these things, but simply by giving what's called a proposal number. So proposal numbers have to be unique, and they have to be bigger than any proposal number that particular proposer has ever used before. Let's say that this one sends out the proposal number of 5. It has to be sent to a majority of acceptors, which could be all of them. Let's say it's all of them. So the first kind of message that is involved in a run of Paxos is a propose message. The acceptors have to respond to the proposed message with what's called a promise. A promise of 5 means I promise to ignore messages with a proposal number of less than 5. So if somebody else comes along and they propose 4 at this point, if some other proposer comes along and they propose 4, the acceptors will ignore it. If somebody else comes along and they propose 6, then the proposers won't ignore it. They have to respond to it. But at this point, they have promised to ignore any message with a proposal number less than 5. At the point when a majority of acceptors have responded with such a promise, which in this diagram is right here. So this message doesn't really matter if it gets there or not, because we only have to hear back from a majority. At this point, now this proposer is free to do the next most important thing that they need to do, right, which is to actually propose a value, right? So at this point, they can send out the value that they want to have accepted by the acceptors. And that is called an accept message. They still have the proposal number of 5 on there, and then they put the value, which might be the string foo. And then, once again, a majority of acceptors, which could be all of them, have to respond with what's called an accepted message. What are some ways in which this could go wrong? Well, if another proposer happened to come in here and talk to these acceptors and get them to promise 6 before this accept message landed on these acceptors, then if that happened, like if proposer 2 came in here and said, okay, maybe acceptors 2 and 3, I propose 6, and they responded by promising 6, in that case, the acceptors would have to ignore these accept messages coming in here because they have a proposal number of only 5. So this is a way in which Paxos might not terminate, right? Because you could have this overlapping of messages. We call this dueling proposers. When there's proposers coming in with messages, getting a promise, then somebody else getting a promise, but nobody's ever able to get their accept messages in time for them to actually hear from a majority of acceptors. So the point, hopefully this doesn't happen, right? So one way to guard against this happening is to try to only have one proposer. So the way in which some consensus protocols operate is to actually elect a leader to begin with, and to have that elected leader be the only proposer. So that's how Raft works, for example. It starts with a leader election phase, and then that elected leader is the only proposer. In Paxos, you can implement it that way. The trouble is that leader election itself involves getting consensus. So leader election also has the risk of not terminating. So you don't get around this termination issue by doing leader election, because it itself might not terminate. If you do get into this situation where you have these dueling proposers, one way around it is to have different random timeouts on the proposers before they decide to propose again. So then hopefully, if you have those different lengths of random timeouts, then the messages will not continue to be interleaved in just the wrong order. So let's talk about what would happen here if this didn't happen. And these acceptors actually do accept. So at this point right here, when these two acceptors have gotten this accept message and sent back this message that they've accepted, this is the point at which consensus has been reached. In other words, if two acceptors accept a particular proposal number and a particular value, from then on, there's no going back from there in Paxos. Even though not everybody knows yet that consensus has been reached, one way or another, that's the value that we're going to end up having consensus on. Now, it could happen that now, after that, proposer 2 comes along and tries to propose 6 here. And of course, because its proposal number is 6, these acceptors are still obligated to respond to that message with a promise. But at that point, because they've already accepted something, they have to tell proposer 2 what it is that they already accepted. So they have to tell it, I accepted foo. And then when proposer 2 sends its own accept message to propose a value, it has to also propose that same value of foo. So proposer 2 is obligated by the Paxos protocol to propose the same value that it's just been told that has already been accepted. And that is how that is how this already accepted value ends up spreading to the rest of the participants. That's Paxos in a nutshell. I recommend going back and watching the lectures where we talked about it in a lot more detail and talked about some of the failure modes and so on. Does that help? I mean, I don't know. When you say you want more information about Paxos, that's my quick overview of it. We could talk a little bit about the big picture stuff. So this notion of this consensus box, right? So I mentioned that Paxos might not terminate, right? And we talked about the properties that every consensus protocol, that we want consensus protocols to satisfy, but that no consensus property or no consensus protocol can satisfy all of. So consensus protocols try to satisfy these properties of validity, which says that the value that ends up being on each of these lines is one of the ones that you started with. Agreement, which says that they agree. And termination, which says that you actually do get something on each of the lines. But no consensus protocol can actually satisfy all three of those in an environment where messages are asynchronous and where crash faults can occur. So Paxos picks termination to be the one that it doesn't guarantee. Some other consensus protocols or some other protocols might choose to pick something else not to do, right? So a protocol might actually choose to satisfy termination and validity, but not agreement. And why would it do that? Well, it might be the case that you're actually okay with the participants disagreeing. So let's say it's a leader election protocol. And you're okay with there being multiple leaders, as long as they're all leaders that were proposed by somebody. So that might be a reason why you might want to choose to have termination and validity, but not agreement. That's not the choice that Paxos makes. Okay, so somebody just asked another question. What's an example of a partially ordered set that's also a totally ordered set? Okay, well, every totally ordered set is also a partially ordered set. So if we just take the natural numbers, right? So what properties does something have to obey in order to be a partially ordered set? So first of all, when we talk about a partially ordered set, we're talking about a set. In this case, we're talking about the set of natural numbers, and we're talking about a binary relation on the elements of that set. So if we talk about this order, let's say it's the less than or equal to ordering on the natural numbers. So there's our set, there's our relation. So let's talk about the properties of that relation. Is it reflexive? In other words, is it the case that for all elements of this set, does the relation relate each of them to each other? Is 2 less than or equal to 2? Is 3 less than or equal to 3? Is 5 million less than or equal to 5 million? Yes, so that one checks out. Is it anti-symmetric? In other words, what does anti-symmetry say? It says that for all A and B, if A is less than or equal to B, and B is less than or equal to A, then A equals B. Well, yeah, that one checks out too, right? These two premises of this are not going to be true unless we're actually talking about the same number, right? So that one checks out. And the last one is transitive. Transitivity says that if you have A, B, and C, A is less than B, and B is less than C, then A is less than or equal to C. And is that one true for natural numbers for this relation? Yeah. Okay, so it meets all the criteria for being a partially ordered set. It so happens that it's also a totally ordered set, which means that every two elements in here are going to have an order according to this. So if we had been talking about a partially ordered set that was not a totally ordered set, for example, set containment. So for example, the subsets of a set. So we know that the empty set is smaller than the set containing A, and we know that the set containing A is smaller than the set containing A and B, and we know that the empty set is smaller than the set containing B, and the set containing B is smaller than the set containing A and B. But these two don't have a relationship like that, right? We can't say that the set containing A is smaller than the set containing B. We can't say the set containing B is smaller than the set containing A. There's not a relationship there. And so this is an example of a partial order that's not a total order, because there are some pairs of elements in here that don't have a relationship. Unlike the natural numbers ordered by this relation, which when we draw out the lattice relating elements to each other, we just get a straight line, because there is in fact a relationship between every two elements. So these properties that make something a partial order are also going to be true of every total order. It's just that total orders have this additional property that every two elements are related, whereas a partial order, it's not guaranteed that every two elements are related by the order. That's the difference. So how does this come up for us? Well, it's these kinds of partial orders that are the most interesting, right? The ones where not every two elements are related. In other words, the partial orders that are not total orders. Because these are the ones where we actually have an interesting problem to solve. Like if one replica thinks that its state is the set containing A, and another replica thinks that its state is the set containing B, if there was an order, if there was a total order, right, then then we might have a way to actually resolve it more meaningfully, right? But just if we just look at the two of them and try to compare them, like we can't really say, well, this one is better than the other, right? So the answer ends up being, like we said, we can choose to take the least upper bound if there's a meaningful least upper bound, or we can just kick both of these to the user and ask the user to figure it out, ask the application to figure it out. Okay, one person is asking if I can talk about upper bounds and least upper bounds and join semi-lattices again. All right, so let's talk about that just briefly. So in a partial order, that's not also a total order, an interesting partial order, one like this one, it's sometimes going to be the case that every two elements have a least upper bound, and sometimes it's not going to be the case. So here's an example of a partial order where not every two elements have a least upper bound. It's the example that we talked about before in class, but I think it's a useful one, so I'll talk about it again. So this is a picture of a Boolean register that could be either empty, or it could be true, or it could be false, right? So this is an example. It's a partial order, right? Because we're saying that empty is less than true in the partial order. So if we want, we can write it like this. Empty is also less than false. But there's not a relationship between true and false, right? So we can also say empty is less than or equal to itself, and true is less than or equal to itself, and false is less than or equal to itself. So it's reflexive, right? Reflexivity checks out. It's also antisymmetric and transitive, vacuously, but it's not the case that every two elements have a least upper bound, because we can't look at these two and find and we can't look at true and false and say, okay, here's something that's at least as big as both, because there isn't anything in there that is. So this corresponds to a scenario in distributed systems where if you have one replica that thinks that the state of something is true, and you have another replica that thinks that the state of something is false, you can't, unless you have something like vector clocks that tell you that that one of those is more recent than the other, then you can't really resolve that conflict in a way that makes sense, right? So this would be a scenario where you might need to tell the user, well, one replica thinks the answer is true and the other one thinks the answer is false. You figure it out. On the other hand, if you did have a meaningful upper bound, so going back to our previous example where we have sets, so an upper bound of A and B in this partial order is of the set containing A and the set containing B is the set containing both A and B. So if you have a set containing, if one replica thinks that the state is the set containing A and another one thinks that the state is the set containing B, then those replicas have a way of meaningfully converging on the same state. And that could either be done by the client or it could be done by the system itself. So the informal claim that I made in class is that if you can guarantee that the states that your replicas can take on are elements of a joined semilattice, and a joined semilattice is just a partial order where every two elements are guaranteed to have what's called a least upper bound. If the states that your replicas can take on are elements of a joined semilattice, then we have a natural way of resolving conflicts without having to run a consensus protocol. That was my informal claim. So what's the difference between an upper bound and a least upper bound? Well, maybe this was part of a bigger system, right, where you could also have a set containing A, B, and C. So the set containing A, B, and C is also an upper bound of the set containing A and the set containing B in the sense that it's bigger than both. So the upper bound of two elements, an upper bound of two elements in a partially ordered set is any element in this set that's at least as big as both. So this element is at least as big as both of those elements, and so is this one. But this one is the least upper bound. This one is more interesting because it's the smallest of all of the upper bounds of these two elements. And the least upper bound is the one that's interesting to us because we want to find a way to resolve the conflict between these two in kind of the most meaningful way possible, right? So it doesn't necessarily mean very much if we resolved every conflict where these sets differ by saying, oh, just throw everything into this set, right? Because then every replica would end up being ABC. Instead, we want to resolve the conflict in the way that's closest to what these individuals said. So that's why the notion of least upper bound is useful to us. About 15 minutes left. This is kind of fun. I'm kind of being forced to talk about all these concepts that are without notes, right? Like normally I prepare for lecture, right? And I have a plan about what I'm going to talk about, and I practice it, and and I have, you know, my own notes, which are typically chicken scratches, but no, this is great. I'm actually being forced to talk about these concepts without any preparation. It's good for me. All right, so in the few minutes that we have remaining, I have some stuff that I want to talk about, but I still want to know if you have more questions for me. They don't necessarily have to be questions about the course. I want to actually address one thing that that came up earlier in the class that I feel a little bit bad about. So I think on the start of course survey, somebody asked me, what is it like being a woman in CS? And I kind of flippantly answered that by saying, well, you have to deal with lots of people asking you what it's like to be a woman in CS. So of course, that's not a complete answer. And I didn't mean to make it sound like it was. But there's a lot of reading material that I can recommend on that topic if you want to know. So please come talk to me about that if you're interested. Or you can just talk to me about my personal experiences. That's fine too. Other thing I want to talk about. So I want to talk a little bit about contextualizing this class and kind of the bigger picture of the world. So we've been talking a lot of, like, going back to the very beginning of this class, what did we say a distributed system was? Well, we said that that one of the characteristics of a distributed system was constant partial failure, right? We said that a distributed system was running on many nodes connected by a network and characterized by this constant partial failure. And what we called the cloud computing philosophy was the philosophy that we would attempt to keep running despite this partial failure. So instead of stopping when we detected a failure, throwing everything out and starting all over, instead we would attempt to keep going in the face of this constant partial failure. And the argument is that that's the only practical approach when you're in a system of many, many thousands or even hundreds of thousands of machines where something is guaranteed to always be failing. So there's no practical way to just start over when there's a failure because you would be always starting over. So instead you have to learn to tolerate those failures. And so we've spent a lot of the class talking about techniques for tolerating failures. And we've talked about, I mentioned several techniques a minute ago for fault tolerance via making copies, whether it's making copies of messages to ensure reliable delivery of messages, making copies of data to guard against machines crashing, or redoing an entire computation to make a copy of the computation, essentially, in order to be tolerant of a computation getting lost. All of these are ways to deal with failure. So I think an important kind of point to keep in mind here is distributed systems are good designs for distributed systems are designed to tolerate failure, but that toleration of failure also makes distributed systems incredibly hard to debug because distributed systems hide their own failures by design. And what I mean by that is when we implement these algorithms that are designed to be tolerant of failure, like let's say it's Paxos. So Paxos will keep working if you have, let's say, 3 acceptors and 1 acceptor fails. It can continue to work in that situation because you only have to hear back from a majority of acceptors in order for Paxos to keep running. And so the other participants in the system, they might not even know that that acceptor failed. They might not know, they have no reason to care. So how would you how would you find out, right, that a failure occurred if your system is designed in a way to hide its own failures? And this is one of the things that makes debugging distributed systems so difficult. So if the system is designed to keep running despite failures, so who are these failures being hidden from, first of all? Well, certainly the failures have to be hidden from those outside the system, right? If you're implementing a key value store and replicas can fail, then clients of that key value store are not supposed to be able to tell that replicas failed, right? At least your system is supposed to be able to withstand a certain amount of failure. And ideally, clients of the system won't notice that there was a failure. Of course, this can't be perfect, right? If all of the replicas fail, then certainly clients are going to notice. But there's some degree of failure that the system is supposed to be designed to withstand. So those outside the system are not supposed to be able to observe these failures. Furthermore, those inside the system who don't know it's broken might not be able to observe the failures. So in Paxos, for instance, if you have one proposer who, let's say, keeps on sending, let's say, I don't know, so let's say we have this this proposer over here who's kind of doomed to always be behind proposer one. And so let's say that like it just keeps on sending proposals that always get ignored because they keep on having just a little bit too low of a proposal number. And so proposer one always wins. And so messages are happening here and then just being summarily ignored by the acceptors. Meanwhile, proposer one is always getting its messages acknowledged and then is getting to actually suggest a value to be accepted and then having it accepted. So these messages are over here are always being ignored. Proposer one has no idea that this is happening over here, right? Proposer one may not know that that proposer two was trying to propose something, and proposer one has no concept of this being unfair, if you will, right? So not only do those outside this system, right? Let's say that this is some kind of replicated data store which is using Paxos, and clients of this system aren't able to observe the failure. Neither is proposer one. Like even from within the system, you might not be able to tell that there's that there's something broken here. In fact, you could argue that this isn't broken. This is exactly how it's supposed to work. And then you could argue that there's an analogy to society here, right? So society is arguably a distributed system, right? Or society is a distributed system. And much like the systems that we've discussed in our class, it's characterized by this constant partial failure. And it's very tolerant of failure in the sense that things can sort of keep working, at least to an external observer, even though parts of the system are horribly broken, right? And not only that, but even those within the system might not be able to observe that other parts of it are broken. Worse yet, some participants might know that it's broken, but have no intention of fixing it because it's serving their needs, right? So what do we do about this, right? If the system is broken and it's designed to hide its own failures, how can you possibly go about fixing it? Well, so one interesting technique that's used for debugging that's kind of gotten a lot of press in the last few years is something called chaos engineering. So chaos engineering, which got a lot of press for its use at Netflix, although they're not the only people who use it. Chaos engineering is causing failures in a live system on purpose to see what bugs are revealed. So for example, causing a replica to fail in a distributed replicated data store, or maybe causing an acceptor to fail in a Paxos cluster, something like that. So this idea of causing failures on purpose in a live system, in a production system, this is the system that's actually streaming your Netflix movies, to see what bugs are revealed. This is a technique to try to reveal those failures that get hidden normally. So this is dangerous, right? It's a little bit risky to do, because you could, if you have a bug, right, you could end up breaking something in production. And the whole point of this chaos engineering is that it has to be done in production, right? Because the production system might have characteristics that whatever testing environment that you have doesn't have. And so actually causing failures in the production system in order to reveal bugs is risky to do, but a very effective way to find bugs. So if I can make a perhaps strained analogy, but one that I think is worth making, to society, well, causing failures in a system on purpose to see what bugs are revealed is kind of what is being done when people carry out civil disobedience. So if you cause a failure that you hope is relatively benign, right? Like in chaos engineering, but it reveals some other failure that then you should fix, then maybe it was worth causing that failure. So by the same, or that same analogy, is that if civil disobedience against police brutality, for example, reveals further police brutality. And so I think this is something that is very much intentional on the part of protesters, right? And so it's dangerous. It's a dangerous technique, because by putting your body out there on the line to try to reveal a way in which the system is broken, it's very dangerous. You're opening yourself up to physical danger to yourself, but you're doing so in order to reveal a way in which the system is broken. And I think this is analogous to chaos engineering, although much more dangerous. And this is not necessarily the only reason to carry out civil disobedience, but it's a way to increase everyone's awareness of the way in which the system is broken. So one thing that you can do as you leave this class is think about the systems that you participate in. Think about the ways in which those systems are hiding their failures from you by design. And think about the way in which you can increase your awareness of the ways in which those systems fail. That's all I have to say. Thank you so much to all of you for being great participants in this course this quarter. Thanks to all of you on Twitch too, for tuning in. And thanks to everybody who left great comments on YouTube. It's meant a lot to me to have this kind of participation from people all around the world. It's not lost on me that the people who are watching on Twitch and the people who are commenting on YouTube, a lot of them are not in the U.S. and it's been very special to me to be able to speak to people around the world, and the fact that you're willing to participate in this class, which might not be in a time zone that's at all convenient for you. So thank you. Thanks to all of you. Thanks to everybody who's taking the class. Please stay in touch. Come talk to me, especially if you're graduating. I would love to know what happens to you next. And take care. Other than that, I'll be on Slack to help answer questions as you're studying for the final exam. And Best wishes. Good luck with everything. Take care.